Hello everybody. Today let us look into integration, and I want to give us an example where we can do it in 3 different ways, the same example. Okay, this is really cool, I think, where of course there's an easier way to do it, but also there are 2 others you'll see that are also applicable to the same example. And here is what we're going to do. We're going to integrate the following function. We're going to say, integral of 4x times x squared plus 1, okay, dx. So let's integrate this, right? What is this integral equal to, right? That's the question that we have, and I'm going to do this in a few different ways. One, let's do this in red. One, let's take this integral, okay, and we're going to do this with the power rule, okay? So let me show what that means. We're going to take this integral, let's bring it down, okay? And by the power rule, well, what's power rule? Going backwards, we know that, let me kind of explain this. So if you take derivative of, we know that d dx, derivative of a polynomial, let's say power of x, x to the n, will give us what? N, right? The coefficient comes from the power, and then x to the power goes down 1 and minus 1, right? Now, if you integrate, of course, you go backwards and you divide by that coefficient, the higher coefficient, by higher power. In other words, look, integral of an x to the n dx, will equal to, and there's always this indefinite integral, will have plus a constant at the end, right? So it's going to be 1 over n plus 1 x to the n plus 1, because you go up in power and you divide to cancel that n plus 1 later. And then plus a constant. And make sure you check that, see, if you differentiate this, just like we did up there, but just with n plus 1 and the 1 over n plus 1, you will indeed get this without the integral back, okay? Remember, they're backwards. So and one way to think about integral is anti-derivative, okay? Undoing the derivative, like an inverse of the derivative. Okay, so power rule is that. All right, let's do this. We take this, let's actually bring it over here, okay? We kind of take it away for a moment. So we're going to take this right here, and we're going to do this. We're going to say, you know what? Here's a power rule. Let's make this a polynomial looking thing. In other words, let's go ahead and say, you know what? It's integral of, but what? Let's multiply it out. Why not, right? Expand it out, distribute it. So like 4x cubed plus a 4x. And this is a linear thing going on here, right? This is a linear property where you can break it down. If you really were doing the steps, let me actually do that. You can break it down into 2 integrals, okay? So you can do this, which a lot of times people don't write that, but formally that's what you would do, where you have this first one and then plus, because this is a summation, it's a linear summation, okay? That's what linearity means. You can basically break a sum within a function into the sum of the functions of the 2 things. Anyway, so there's this, okay, and we have integral of 4x cubed turns out to be x fourth plus a constant 1, then plus 4x from 2x squared, if you think about it. We have the power rule, okay? Plus, let's say another constant c2, and we can bring this all together into x to the 4th plus a 2x squared, and then plus a constant, right? Constants plus constant, they're going to be constants, some kind of constant, right? And that is it. Then we're done. However, there's another way to do this. Let's see. Let's look at what is called the U substitution. So what U substitution is, okay, basically it is like undoing the chain rule of differentiation. So let's look at that. U substitution. Well, the chain rule, what's chain rule? That's a very big rule. This is how you do derivatives of almost anything, right? Chain rule will say that if you have a d dx of the composition of functions f of, or f op, but let's do f of g of x, that's the definition of f op g of x, and that's equal to then the derivative of the outside function of the inside one, right? And then times, of course, the derivative of the inside one, okay? Don't forget that. So that's the chain rule, and if we do, let's say the use of substitution, what happens is you can undo, let me just say undo the chain rule. Let me show you how that works. Undo the chain rule, undoing the chain rule. this chain rule. So let's go directly at this problem. We had again, we have to, so we go this way, right? Where we have, here's what we're looking for. Now you know what? We're gonna let this equal to u. Let u equal to this x squared plus 1. And this is a reason why. You have to look for what can you do that if you take derivative of u, kind of like this g prime of x, okay? That it will still be there. You'll still have that incorporated into the whole function, okay, to make it easier for us to simplify it, really. And so look, du, you can even do du dx, derivative, is equal to 2x, right? So what is du by itself? It's 2x dx. And you can see that there's a, what is x dx then, right? See that right there? Well, that's going to be 1/2 du, right? So 1/2 du by 2 both sides. That's that. You see, so dx dx, you can put 1/2 du. Okay, cool. So we have equals to, and the 4 can come out if you like, but let's keep it in for a second. Integral of 4, and then we have x squared plus 1 is just u, and then oh, it's a 1/2 du, right? Okay, that's cool, because this is actually integral of what? 2 u du, right? And that comes from directly u squared, right? Plus a constant. Let's say plus a constant c3, since we already used c1 and c2. And then let's square. What is u? Let's substitute back. Okay, this is u substitution, right? Substitute back for u the x squared plus 1, and we're squaring it, right? Plus a constant c3, okay, equals 2. Let me put a little bar here so we're not confused. Okay, that's a little kind of something from on the side that was there, right? Let's make sure we understand this is not part of the solution here. And there's that, and then let's do this again. I like the little separators, okay? So here we are, it's on the left side. Now on the right side, we're actually solving this integral, and we have this, and then what is x squared plus 1 squared plus c3? Well, if we square the binomial, we get x to the 4th plus a 2x squared plus a 1 plus c3, and that's going to be, you can just put 1, which is a constant, and c3 is a constant, into 1 plus 2 squared and 1 constant. And it's the same thing, right? So we got the same thing, x to the 4th plus 2x squared plus c, and the same thing was up there, right? Cool. And let me show you one more method. This is, usually you would not use this method for this problem, but you can, okay? And let me show you what you would do here. What you can do is, let me copy again this integral, okay? Oops. Let's do this. I'm going to copy this, okay? Place it down here, okay? But before that, let me remind you something else. It's called integration by parts. Let's use a different color now. Let's do this one. So integration by parts. What in the world is integration by parts? Let's do the other. So we're going to do that in this example. Usually integrals are not done by all 3 methods. It's just not, most of the time 1 or 2 will be the sufficient, or I mean, will only be applicable. But here, this problem, we can even do the 3rd one, which is integration by parts. Let me say integrating by parts, okay, integration by parts. What that is more like the going back on the product rule. So undoing, okay, that was undoing, remember, power rule, undoing the chain rule, now undoing product rule of differentiation. So product rule says what? If you do d dx of the product of functions, okay, or even like, let's say u times v, let's keep the x out of that. So it's u of x and v of x, but we'll just put uv times u of x times v of x, right? You get the derivative of the first one times just derivative times just the second function u prime v, plus copy the first function and then multiply by the derivative of the second. So that's one way to write the product rule of differentiation. So if you think about it, let's lower this. We'll put it back later. What happens is if you integrate everything there, let me show you. Let's integrate everything there. So you have get rid of the d dx basically. So uv will equal to, and you'll really get what? You'll get integral of, that's a v du, because that u prime is like a du there, the dx's go away. Here, let me show you quickly in case you are so confused for this. Let me show you. So get rid of the dx everywhere. So look, let's rewrite it this way. d dx of uv, right? is equal to d, what is u prime? It's du dx times v. Let's show it. It's a good example to look at. Plus dv dx is what kind of a one rather indirect, informal way of proving the integration by parts. Okay, but if you do a little bit more formality with continuity, with all this, then you actually, very similar approach does prove it. Okay. Anyway, so look, multiply everything by dx. That's a little bit, not informal, let's say, but look. So you have d of uv is equal to v du, I'm going to rewrite it in that order, plus a u dv, right? The x is canceled, dx is canceled. And then if you integrate both sides, okay, you get just uv left, okay, equals to integral of v du, okay? That's what, that's right there, that integral of du. V is just integral of, it's just uv then. Integrate both sides. This goes here, and this goes plus an integral of u dv. Okay, and then you're like, well, what's the point? Well, the point is if you solve for integral u dv, integral of u dv, that's how we initially see an integral usually. We can also write it as, if you subtract this from the right side to the left side, right, and just solving for this, it's going to be uv minus integral of v du. This is integration by parts. So let's figure out how do we apply it. And right there's a method I usually use the word liate, logarithm, inverse, algebraic, trigonometric, exponential, to go from left to right. We're picking the u. I know I'm really using it here, but if there's sine and e to the x, what do we use for u? What do we use for v? So going this way, you let u equal, okay? And then going this way you want dv to equal, okay? Usually, almost always, okay? So this is logarithm, and this is inverse type of function, and this is let's say arc sine, arc cosine. This is algebraic, some power like x squared, algebraic, and then this is trigonometric, like sine, cosine, tangent, and this is exponential, right? E to the x, okay, exponential. Exponent, let's just do that. Well, exponential, right? It's not exponent. So let's just try to do it. Okay, that's the idea. Just remember that if you ever have to in the long run. But look, let's see if it copies and pastes what we needed to. Yes, there it is. Let's try this. Again, this is algebraic. Everything's algebraic. What I'm going to do is to make it simpler. Ready? I'm going to say, you know what? Let u equal x squared plus 1. Because what's du going to equal to? If you differentiate everything, you get a 2x, right? Plus a constant 0, plus a 0, constant goes to 0, and then a dx, of course. I'll put the dx to the right side already. And let's let dv equal to whatever's left, 4x dx. So where does that come from? V equaling to 2x. Okay, cool. So what we do now is we say, you know what? It's going to equal to integral what? Let's write it again. dx is integral uv, if you think about it, right? Is integral is equal to uv. Well, what's u and what's v? U is x squared plus 1. V is 2x squared. Okay. Minus integral, that's a u, that's a v. Minus integral of, remember what I told you? V du. So what's integral of, let me raise this so we're not confused in this notation here. With this, what I have written below. So look, this is kind of what's going on. Let me make it a little smaller here. So okay, you see this anyway. Let me delete it so we're not going to confuse anybody. But look, integral of, what is this? V, which is now 2x squared. And then what's du? That's going to be the 2x dx. Cool, right? Okay, so this should work. May look, the whole point, maybe kind of missing the point that integration by parts can make things a lot easier, actually. It's just this example can be even done with power rule going backwards. That's why it's not really needed. But I wanted to show you that all three are applicable to this problem. And that I think is really cool. And then you can maybe learn how to do all of these types of integrations from this example. Okay, so anyway, we have this. Let's continue now. And of course, you still see we're going to be using a little bit of backwards power rule. But what is this? This is 2x to the 4th plus a 2x squared. And then this is an indefinite integral, so we have minus integral of what? 4x cubed, right? dx. Well, this is equal to 2x to the fourth minus plus a 2x squared, and then that's minus a what? That's going to come from x to the fourth plus a constant. Let's call it c4 because we haven't used that one yet, right? Okay, so we have the x to the fourths. There's a one that goes away, so you just have x to the fourth left, right? You have this one with that one, so only one is left. And then x to the power 2, and then minus the c4, and just put, and that exactly is what we had for the other two approaches, right? X to the fourth plus 2x squared and plus a constant. So I hope this is something really interesting for some of you. I find it kind of fascinating that there are problems that can be done in multiple ways. Of course, this is the one I would do the first approach in red, right? I would do just going back in the power rule right here. That's so fast, so easy, right, in a sense. But then the U substitution maybe is a little easier than, let's say, the last one. But at the same time, all of these have meaning, okay? So make sure you understand each of these three, because you need to know all of these three methods rather well to be integrating a lot of different important functions. Okay? Thank you so much for watching. Please comment and have a great day.